Hi guys, welcome to this video. I'll be walking you through the Specimen Paper 1 of Physics A, OCR, and let's get started with Section A. So the question number 1 says that the length x is given to us as 50 millimeters plus or minus 2 millimeters, length y is 100 millimeters plus or minus 6 millimeters. The length z is given by this formula here, and we're asked to write down what is the best estimate for the uncertainty in z. So for this, we have to consider the upper and the lower bounds in x and y in order to work out the uncertainty in z. So for the upper bound, it will be 52 millimeters in x, and the lower bound will be 48. And over here it will be 106, and otherwise 94 for the lower bound. So to work out the highest possible value of z, we are going to use the upper bound in y, so as to get the biggest difference, okay, which is 106, minus the lower bound in x, which is 48, and that will give us 58 millimeters. So this is the upper, the highest value, okay, so the highest value. And for the lowest value, similarly, we're going to look at the lowest value of y, which is 94. Okay, so this is the low. Okay, minus the, I'm going to go for 52, okay, as the difference will be the smallest, and that will give me 42, okay, millimeters. So now the uncertainty is given to us as half the range, okay, half the range, and so it's just going to be half of 58 minus 42, or 16, so that will be therefore D. So in questions like this, okay, just be careful when it comes to them providing two sets of the same sort of measurements, okay, whether it's millimeters or it's voltage. Do consider this formula right here that I've written down for uncertainty in the actual value, which is set by a given formula. Now for question number 2, we are given that a 2 meters rigid rod with negligible weight is subjected to forces in 3 different ways as shown in diagrams 1, 2 and 3. And for the rod to be in equilibrium, which of the diagrams above is or are correct? So for the first one, the two forces acting are on either ends, okay, and they will balance out the force acting over here in the center, 2 newtons. So number 1, the rod will stay in equilibrium, it won't move, and so number 1 is correct. Number 2 is we've got two forces of 2 newtons each on either ends, but bear this in mind that this will be a coupling effect. It's very much like when you are driving using 2 hands on your steering wheel. So it will make it rotate, okay, and therefore 2 is out of 2 is not correct. So, well, that just leaves us with D being the answer. Okay, so only the first one is correct. Okay, now question number 3 says the potential difference across a resistor is 12 volts and the power dissipated is 6 watts. Which statement is correct? So A, the charge passing through the resistor in 1 second is 2 coulombs. Well, let's find out so what the current is, because 1 second, 2 coulombs, that's 2 coulombs per second, which refers to the current, but current is given by power divided by voltage, or in other words 6 divided by 12, so that is incorrect. Okay, the current happens to be 0.5 amps. Then the resistor transfers 6 joules for each coulomb per passing through the resistor. So when it says 6 joules per coulomb, it just means 6 joules per coulomb, like that. Okay, now that technically over here is 6 watts. Now 6 watts is actually joules per second, okay, not joules per coulomb. So B is also out. Then the resistor transfers 12 joules in 2 seconds. So 12 divided by 2, okay, is 0.6, and that refers to watts, so C is the correct answer. Then question number 4. A spring with force constant 0.1 newtons per centimeter is placed in series with another one of 0.2 newtons per centimeter. These are then placed in parallel with an identical set of springs as shown, and a force of 0.6 newtons is applied. What distance does X move down when 0.6 newtons force is applied? So we need to remember the value of the spring constant, how it changes in series versus in parallel. So when it comes to these two springs over here with 0.1 and 0.2 newtons per centimeter, the overall spring constant in series is given by 1 over k equals 1 over k1 plus 1 over k2. So that gives me basically, 1 over 0.1 plus 1 over 0.2. In other words, it gives me 15, okay, or rather, k is 1 over 15, okay, the overall. And now that we're dealing with a parallel combination altogether with the same set on this side as well, the overall, so this is in series, okay, just to be clear, okay, the overall k value in parallel is given to us as k1 plus k2, okay, so that means that it's just 2 times this 1 over 15, or just 2 over 15 is the overall k, or the spring constant value. Okay, now we are given that the force of 0.6 newtons is applied, and we know that F is equal to k times x. So therefore x is equal to 0.6 over 2 over 15, which ends up giving us 4.5 centimeters, hence C is the answer. So with question number 5 now, we are given that a group of civil engineers are assessing whether or not to use solid concrete pillars or hollow metal tubes to support a building. One such tube is shown below, and the tube is placed on a horizontal surface, and the tube is made of metal of thickness T. The total height is h, and the mean internal radius is r, where r is much bigger than the thickness of the tube. A heavy metal block of mass m is placed on top of the tube. What is the approximate pressure acting on the tube? Now, let's say that this one over here, what we have is it's a hollow metal tube, okay? Now, pressure is equal to force over area. So if it is hollow, the force, or the mass that we are placing will fit right in, okay? So it would exert a pressure on the circumference of this tube. So therefore, weight obviously being the force, mg, of the mass block, metal block, divided by the area on which the force is being exerted, happens to be along the circumference, okay, so 2 pi r times by the thickness, okay, which is T. So the correct answer over here will be A. Okay, so that's question number 5 done. Let's move on to question number 6. It says a train consisting of 6 trucks of mass 6 times 10 to the power of 4 kilograms is pulled at a constant speed by a locomotive of mass 24 times 10 to the power of 4 kilograms along a straight horizontal track, and the horizontal force resisting the motion is 4,000 newtons. The coupling between the trucks 2 and 3 snaps, and what is the initial acceleration of the locomotive? So there's a couple of things going on. So initially, okay, there are 6 trucks, and they all have a resistance of 4,000 newtons. Okay, so 6 times 4,000 is the overall resistive force. Now that the coupling has broken, okay, after breaking, we know that there are only 2 trucks left with a, therefore, overall resistive force of 8,000 newtons. So basically the difference between the two, okay, is going to help us find out the acceleration, the initial acceleration using F equals ma. Okay, the overall force is just simply 6 minus 2, or rather 4 times 4,000, okay, so 16,000 newtons divided by the mass overall. Now that we have, you know, 2 trucks, okay, plus the mass of the locomotive, so 2 trucks is just going to be 12 times 10 to the 4. I know it's not standard form, but 24 plus 12 is 36 kilograms times 10 to the power of 4. And when you put that in the calculator, you end up getting B as the answer. So watch out for questions like this. They sound a little bit tricky, but if you lay it out step by step, initial versus final, that really helps with such questions. So question number 7 now. It's given that when a sandbag is dropped from a balloon hovering 1.3 meters above the ground, it hits the ground at 5 meters per second. On another occasion, the sandbag is released from the balloon when it's rising at 7 meters per second, when 1.3 meters above the ground. There's a crosswind of 5 meters per second. And what is the speed at which the sandbag will hit the ground? So when it says speed, speed is the magnitude. Okay, so the speed is going to be equal to the square root of the final velocity along the horizontal plane, as well as the final velocity along the vertical plane. So what we are assuming over here is that if there is crosswinds going at 5 meters per second like this, it will just be you know, landing like this. The bag will be landing like this. Okay, so we're going to assume that there is no air resistance. Therefore, the final horizontal velocity is going to be the same as the initial horizontal velocity, which is 5 meters per second. Okay, now as for the vertical plane, we can work that out using SUVAT. So we know that v squared is equal to u squared plus 2as. Now, along the y-axis, or the vertical plane, the balloon was rising at 7 meters per second, and we are dealing with downwards motion. So I'm just gonna, it's not gonna change the overall answer, but I'm just gonna put a minus in front of 7. Okay, just to get the physics straight. Okay, so that'll be that, and then 2 times 9.8 times by the height, which is 1.3 meters. So I'm just going to leave it unsquared. I'm just going to leave it in a squared form, which is something along those lines. Okay, and now therefore the speed is just going to be 5 squared plus 74.48 square rooted, which gives me C as the answer. Okay, so it's just going to be 5 squared plus 74.48, just to be clear, and that will be the answer. So that's question number 7 done. Let's move on to question number 8. It says a piece of flat A4 paper is dropped and falls to the floor. The same piece of paper is then made into a ball and dropped again. What is the following? Which of the following will change in the second situation? Well, it will be the time to reach terminal velocity because of the dimensions. Okay, the air resistance will act differently. There will be smaller amount of air resistance acting, you know, initially until it basically reaches its terminal velocity, which will be at a different time. So C is the answer. Question number 9. It says a small amount of copper is heated in a container and copper starts to melt. So which of the statement about melting of copper is correct? Temperature is constant and the kinetic energy of copper atoms increases. Well, yes, temperature is constant, but it is not the kinetic energy of the copper atoms that increases. It's the potential energy that increases, because copper as a metal has atoms fixed in their positions. Okay, so it is the potential energy that tends to increase, but the temperature remains constant when it's melting. So C is the answer. Question number 10 talks about what are the correct units of specific heat capacity. So we know specific heat capacity is written as joules per kilogram per Kelvin. And joules can be written as kilograms meter squared per second squared. So if I just tidy this up, kilograms and per kilogram, they get cancelled, and that leaves me with A as the answer. Question number 11. So I can never say this star name, so I'm just gonna Betelgeuse, I don't know, sorry, apologies. Well, it's a star in the constellation of Orion, which astronomers think could undergo a supernova explosion. What could it evolve into following the supernova stage? So the only answer, correct option over here is B, okay? You just need to know the sequence of, or the life cycle of stars. So I know B is the correct answer. I'm going to just leave it there. So question number 12 talks about stars emitting EM radiation. A graph of intensity against wavelength is given for a main sequence star. Which statement is correct as the main sequence star evolves into a red giant? So a red giant, as you should all know, is a cooler star than the main sequence star. And the wavelength is inversely proportional to temperature. So as the star is cooler, the wavelength will be higher. So that leaves us with D being the answer. Okay, so question number 13. It says, when the light from a star is passed through a diffraction grating, it forms a spectrum. Which of the following statements is or are correct? Light emitted from the surface of a star would form a continuous spectrum. Yes, indeed, it would. Then light received from the sun has dark lines across a spectrum which corresponds to the absorption of certain wavelengths by the atoms in the Earth's atmosphere. Well, the statement is correct up until the point here, okay, by the atoms in atmosphere of the Earth. It doesn't happen in Earth's atmosphere, it happens as the light passes through the sun's atmosphere, where the gases are a little bit cooler and they absorb there's some absorption going on of certain wavelengths by the gaseous atoms. So it is, therefore 2 is incorrect, which leaves me with D being my answer. Okay, so only the first one is correct. Well, that's the only option in this case, because the others are where 2 is correct and 2 isn't correct. So as for just for the sake of number 3, it says a photon is in an emission spectrum occurs when an electron moves from a low to a higher energy level. That's definitely incorrect, because a photon is emitted when an electron moves down from a higher to a lower energy level. So just for the sake of it, so yeah, D is the option. Question number 14. It says a star has a surface temperature of 3000 degrees Celsius and luminosity L. Another star of identical size has surface temperature of 2500 degrees Celsius. What is the luminosity of the second star in terms of L? So we know that luminosity is directly proportional to the 4th power of temperature, or T to the power of 4. So I can just put it in the form of a ratio. Okay, so the luminosity of the second star over the luminosity of the first star is equal to the temperature in, of course, kelvins. Okay, just be careful here. So the second star has a temperature of that, which turns out to be 2773 kelvins, over the temperature of the initial, which is 3273 kelvins, to the power of 4, and that therefore gives me 0.52 luminosity. B is my answer. So now for question number 15. we've been given that scientists are planning to launch a rocket from the surface of the Earth into an orbit at a distance of 18,000 kilometers above the center of the Earth. Okay, that's important. The radius of the Earth is 6,400 kilometers and the mass is 6 times 10 to the 24. What is the minimum work done to move 150 kilos of this rocket into this particular orbit? So this question isn't that straightforward at all. You have to really be careful about what are the energy changes happening, or what is the overall energy at in the orbit. Okay, so if I just say that you have the Earth and the satellite is sitting on the surface, okay, it would have some potential energy compared to from the center, okay, at the radius of 6,400 kilometers. Then as it is launched into space, into the orbit of 1,800 kilometers from the center, it would have some kinetic energy and some gravitational potential energy. So bearing that in mind, okay, the overall energy change will be, or the minimum amount of work done will be, therefore, the total energy, okay, at these 2 points. All right, so in terms of the surface, we're going to have gravitational potential energy, which is minus gmm over r, okay, and this is the surface, so I'll just put that down. And then we are also going to have the overall energy, so E total at the orbit is going to be now the energy, the kinetic energy, okay, plus the gravitational potential energy. So the kinetic energy plus E grav. Okay. Now we know that it's half mv squared. Okay, but we are using in terms of gravitational, like the masses, etc. So just bear in mind that the formula, I mean, I can derive it right here on the side. The kinetic energy is, we know, half mv squared, okay? And the velocity or the speed is given to us by gm over r, okay, just without the square root, okay? I don't know whether this formula is actually given to us in the formula booklet. Do check, otherwise I suggest you learn it. So v squared right here is essentially that, okay? So it is half gmm over r, and the gravitational potential energy is minus gmm over r. So overall the energy is minus gmm over 2r. Okay, so this is the energy at 18,000 kilometers, okay, from the center. So once you have that and you consider, therefore, the minimum work done now, I think this is one of the longest questions in this particular paper. So work done is equal to the energy, the total energy minus gmm over 2r plus, or plus, because it's gonna be minus because it's the difference between, okay, so plus, yes, it will be gmm over r at the surface. So these two values are completely different, okay, r at the surface and at in the orbit. So we can just simply really simplify this in terms of taking out gmm and leaving it as 1 over 2r plus 1 over r at the surface again. And when we put that all down, we end up getting B as the answer. So that is quite a wild question. It's got a lot of work involved, and but this is how you consider doing this question. So I believe that's the end of section A. Let's get started with section B now. Question number 16, part A, says two cars, A and B, are travelling clockwise at constant speeds around the track, shown in figure 16.1. The track consists of two straight parallel sections, each of length 200 meters, the ends being joined by semicircular sections of diameter 80 meters. The speed of A is 20 meters per second and that of B is 23 meters per second. Calculate the time for A to complete one lap of the track. Okay, so for A, we need to figure out what is the distance that it travels because we know the speed. So the distance traveled is, of course, the 200 and another 200, right? So this is like over here 200, over here as well it'll be 200, plus these two semicircles which make up a circle, and the circumference of a circle is given by pi d. So pi d plus 400 will give me 651.33 meters of distance, and therefore time taken is 651.33 over the speed of A, which is 20 meters per second, and that gives me 33 seconds for one lap. Now, part II says, starting from the positions shown in figure 16.1, determine the shorter of the two distances along the track between A and B immediately after A has completed one lap. So we need to figure out with the given with the given time that A travels or A completes one lap, how far does B travel? Okay, so that is basically in those 33 seconds, how far does B actually travel? Okay, so I'm just going to call it distance x, okay, of B, is its speed, which is 23 meters per second, times by the unrounded value, I think I had 32.6 seconds, which gives me 749.8 meters. Okay, now that is slightly over the one lap, the distance of one round. Okay, so therefore the extra that B has traveled, okay, B has traveled extra distance, okay, is 749.8 minus 651.3, which is 98.5 meters. Okay, so now it's therefore going to be, it's already, so B would have completed a round already, okay, around the track. It would go like this, and then it would cover an extra distance of, well, 98.5 meters. And we know that this is 100 and this is also 100. So perhaps it's somewhere here, okay, when A has completed one lap. So now we just need to find out that distance between, which is, if I just highlight, so this extra distance, okay, and this distance, which is the semicircular arc, okay, plus the distance that A has covered, A has reached back, okay, at that point. So we know that because this whole thing over here is 100 meters and this bit is 98.5 meters, therefore this little bit over here is going to be 1.5 meters. Okay, so that's that, plus the pi d over 2 situation. Okay, so that's, and then plus 100. So I'm just going to write that down. So we have pi d over 2 plus 1.5 plus 100, and that ends up giving me 227. I don't know what's happening there. Okay, 227 meters as a final answer. So let's move on to part B now. Cars A and B are now on a straight road with car A moving at 22 meters per second and car B is at rest. As car A passes car B, B accelerates to from rest in the same direction at this much rate for 16 seconds and then moves with a constant velocity. Now, we've been given the graph for car A, okie doke, and we're given that the time t equals 0 is taken when the cars are alongside. Sketch the graph of velocity against time for car B on this particular graph. So we just need to figure out what is the final velocity. So v is equal to u plus 80, which is 1.5 times by 16, as u is 0, which turns out to be 24 meters per second, so in 16 seconds. So I'm going to go ahead and 1, 2, 3, 4, there. Okay, so that's that, and then it just goes constant velocity, and this is for B. Okie doke. Now, next part says, determine the time taken for car B to be alongside car A. Now, let's say that time is t seconds, okay, and we know that they would be alongside each other when the distance covered by them is the same, when they've covered the same distance. So we need to look, therefore, at the area under the sections of A and B. So if I just basically pull this down, I can use trapezium as well, that's fine too, but I'll just do it in bits and bobs. So basically what I have is the area of this triangle, okay, which is half times 24 times by 16, which gives me 192 meters. And then I would have this area as well, this rectangular area, for which I don't really know how far to go. So I'm just gonna say it's the area of this rectangular section for time t seconds. Okay, the difference on the x-axis is going to be t minus 16. Okay, so it'll be the height, which is 24 meters per second, and t minus 16. So those two quantities now can be added together, okay, and I would end up getting 24t minus 192 meters for car B. Similarly for car A, well, that's easier because it is going at 22 meters per second for t seconds. So for car A, the distance traveled is 22t. And because these two distances are the same, they are going to be equated to find t. And I am going to get 2t as 192 or t as 96 seconds. That was a good question. Okay, right, let's move on to question number 17. Part A says, a cyclist moves along a horizontal road. She pushes on the pedals with constant power of 250 watts. The mass of the cyclist and the bicycle is 85 kilos and the total drag force is 0.4 v squared, where v is the speed of the cyclist. Calculate the energy provided by the cyclist each minute when the overall efficiency is 65%. So we can work out the energy for a minute, which is 60 seconds, and that is just power times time. So 15,000 joules is the input, okay? And we know it's 65% efficient. So therefore, the energy will be, the required energy will be 15,000 divided by 0.65, and that gives me 2.3 times 10 to the power of 4 joules. For II, we are to calculate the drag force and hence the instantaneous acceleration of the cyclist when the speed is 6 meters per second. Okay, so I can work out the drag force, which is 0.4 times by 6 squared, and that is 14.4 newtons. Now, I need to work out the instantaneous acceleration, for which I have to consider the resultant force. Okay, so I'm going to calculate the forward force, which is due to the power of 250 watts. So power is equal to force times velocity. So F is equal to 250 over 6, which is 41.7 newtons. So the acceleration is going to be equal to 41.7 minus 14.4 over the mass of the cyclist and the bicycle, which is 85 kilograms, and that gives me 0.32 meters per second squared. For part B, it says that the cyclist now moves up a slope at a constant speed of 6 meters per second and continues to exert a power of 250 watts on the pedals. And we need to draw arrows on 17.1 to represent the forces acting on P, labeling each force with the arrow it represents. So the first one is obviously the weight, and which is like that. The forward force, I'm just going to call it forward force, that's due to obviously the power, the drag, which opposes the motion, and the normal force, which is perpendicularly upwards. So that's my forces done. Now, part II says calculate the angle of the slope to the horizontal. So I just need to consider the forces here. Resolving the weight will help me out to get what's happening along the plane. Okay, so I know that there's a force acting this way. I should probably draw it as a triangle, as a lot of students prefer that. And then there's a force acting this way. Okay, so basically that way and then that way. So that is going to be W sine theta. Okay, and this is of course the force, the weight essentially, and this is theta. Okay, just to be clear. So W sine theta, and along with the drag that's acting and opposing the overall force. Now, therefore, what we have to consider is F equals ma, of course, okay, but we know that the forward is the overall force is 41.7, which equals the 14.4 newtons of drag plus the 85g sine theta of the component of the weight. So therefore, sine theta, or rather theta, ends up being 1.9 degrees. So that's my answer right here. Okay, let's move on to part C. The cyclist continues to move up the slope at 6 meters per second and approaches a gap of width 2.5 meters. And we are given that a student has calculated that the cyclist will be able to clear the gap and land on the other side, whereas another student suggests that this calculation has assumed that there is no drag and has not accounted for the effect caused by the front wheel losing contact with the slope before the rear wheel. Without any calculation, we need to discuss how drag and the front wheel losing contact with the slope will affect the motion, and explain how these might affect the size of the gap that could be crossed successfully. So when it comes to drag, if we are not considering drag, or if we now consider drag, the drag will reduce the velocity, number one, okay, or it would increase the time. And number two, if the front wheel loses contact with a slope, it means that the wheel will therefore have some torque, okay, causing the bike to have some moment, okay, it will have a rotational effect on it. And this rotation will cause the height to reduce, okay, the bike will therefore be at a lower level, and what that means is that the gap should be made smaller, indeed, okay, for the cyclist to reach successfully on the other side. The width of this gap over here should be made smaller. So that's that. 18 now. It says, part A says that a group of scientists have designed an alloy which is less dense than copper but may have similar mechanical properties. A researcher is given the task to determine the Young modulus of this alloy in the form of a wire. Write down a plan of how the researcher could do this in a lab to obtain accurate results, including the equipment used and any safety precautions necessary. So, just as some background information, we know that Young modulus, E, is essentially stress over strain, which in other words can be written as F times L over A times delta L, where F is the force, L is the length, original length, A is the area of the cross section of the wire, and delta L is the extension. So if we were to draw a graph of stress versus strain, the gradient will give us the answer. And so we can, let's get a drawing for this. I suck at drawing, so I'm just going to try and get a diagram there. Okay, lovely. Okay, there we go. That will do the job. So I can just say it's, instead of copper wire, I can just say the alloy wire that we are trying to study. So in terms of measurements that we will take, I'm going to write them down. So of course we are going to have to use vernier caliper to measure the diameter of the wire at different places and then average them out and find the radius and then find the area, pi r squared. So A is basically done, okay, and then we are going to also have to change the measure the length, okay, of the wire and stretch it as much as possible using the G clamp, and hold it in place so that there is tension. It's tightly clamped, okay, between the two sections. And the wire should be made as long as possible, usually about 3 meters we tend to use. And then we have the weights, which are added on as well until the wire is just taut, and then we make an initial reading of the marker. So we can then add on more weights and read off the extension and record them as well. Now, in terms of safety measures, we need to think about making sure that the load is not, it doesn't come down crashing. So we can use a crash pad under the weights, wear goggles just in case the wire breaks, to protect your eyes. Don't put your feet under the weights, of course. And in terms of the analysis, we just need to get the graph of stress versus strain, and get the gradient of that straight line, and that would be giving us the value of E, or Young modulus. Part B, I. State the meaning of elastic and plastic behavior. That's an easy question. Elastic is simply when the material returns to its original shape, okay, when the weight or the load is removed, okay, so material returns to its original shape when unloaded, whereas plastic behavior is when the material permanently changes shape and doesn't come back to its original shape, therefore. And worth remembering these definitions because they are relatively easy. Now, for the next part, it says, repeatedly stretching and releasing rubber warms it up. And we're given a force extension graph. Rubber is an ideal material for aeroplane tires. Use the information provided, discuss the behavior and the properties of rubber and how its properties minimize the risk of, the risks when the plane lands. So we can see that as the graph shows, rubber returns to its original shape. When unloaded, it has an elastic property, or it behaves elastically. And we can also see that when energy is energy stored, of course, is the area under the graph, and during unloading, or when it lands, some of the kinetic energy gets transferred into thermal energy store due to friction and between the tires and the road. So this will therefore reduce the bouncing effect, which is ideal and safer for the passengers in the plane. Okay, so that's what I'm going to say. Question number 19 says, a flat circular disc moves across a horizontal table with negligible friction. Figure 19.1 shows the disc X of mass 50 grams subjected to a force F, shows variation of force with time. Okay, let's look at the first part. It says the disc is initially at rest. Calculate the change in velocity of the disc caused by the force F. So we know that force times delta t, or the impulse, is equal to the change in momentum, or mass times the change in velocity in this case, which is what we are calculating. And the force times delta t is essentially the area under the graph, which can be easily calculated using the formula for triangle, and this happens to be 1.8 newtons. So half times 1.8 times by 60 milliseconds, which is 0.06, divided by the mass, which is 50 grams, and so 0.05, and that will give me change in velocity as 1.1 meters per second. So for part B, it says, in a different experiment, disk X moves at 1.5 meters per second, collides elastically with two other disks Y and Z, which are touching and at rest. All disks are identical. The positions of the disks are shown below, and we need to put arrows to show the relative magnitude and the direction of forces which act on disk Y during the collision. Well, that's relatively simple. The force exerted will be equal and on both sides, so they will be of equal length arrows, like so. State the resultant force on Y during the collision. It will be 0. Now, show that after elastic collision, X is at rest and Z moves at a velocity of 1.5 meters per second. So elastic collision is where the kinetic energy is conserved. And so if I was to think about this question in terms of perhaps momentum and kinetic energy conservation, I can work this out. So I know that initial kinetic energy, okay, is just due to the motion of a disk X, okay, because that's the only thing that's moving. So I can say it's half mux squared, which is equal to the kinetic energy of X and Z, okay, as Y doesn't move. So we can say that half mvx squared plus half mvz squared. And because the mass is identical, we can safely narrow it down just in terms of the velocities, like so. Now, similarly, the momentum is conserved as well. So the initial momentum is that due to disk X, which equals the momentum of disk the final momentum of disk X, which is m times Vx plus m times Vz. And so again, it simplifies to Ux being equal to Vx plus Vz. Now, I can just solve this equation and this equation simultaneously and get my answer for Vx and Vz. Okay, so I'm going to square the second equation so as to get a whole squared, in the two terms. Okay, so I'm just substituting 2 into 1. So Vx squared plus Vz squared. When you expand this out, things will cancel out quite a lot, and you'll be left with simply 2Vx Vz, okay, which is equal to 0, okay, which means that therefore if Vz is say 1.5 meters per second, okay, then Vx is going to be equal to 0. One of the quantities must be equal to 0. And in this case, if Vx comes to rest, then Vz has to be 1.5 meters per second. So you can do that also by just using one of the two equations as well, but that's where I'm going to leave it. Okay, so that's question number III done. Let's move on to question number 20. It says that the apparatus shown in figure 20.1 is used to investigate the variation of the product PV with temperature in the range of 20 to 100 degrees Celsius. The pressure exerted by the air is P and the volume of air inside the flask is V. Describe how this experiment can be set up and used to ensure accurate results. So, majority of the conical flask should be submerged in water. That's it, to ensure that all the heat is obviously transferred from the water directly to the flask. Then you could also say that the rubber tubing, the volume, should be negligible compared to that of the flask. And then you have to make sure that you stir the water for uniform distribution of energy after removing the Bunsen burner and giving enough time to conduct heat from glass to the glass of the flask to the air inside. Okay, so that would ensure accurate results. Part B says an investigation similar to that shown in figure 20.1 gives measurements of the pressure P and volume V and temperature theta in degrees Celsius of a fixed mass of gas. The results are shown to plot the graph of PV against theta, and we need to explain in terms of the motion of the particles why the graph does not go through the origin. Well, that's because at 0 degrees Celsius, the particles still have some kinetic energy, okay? So they are therefore still moving. And so as they have some kinetic energy, okay? So therefore they would exert pressure on each other and on the container walls due to the collisions, okay? So on the container due to the collisions. So that's why it is not going to be 0. Then it further says that the mass of a gas particle is 4.7 times 10 to the minus 23 kilograms. Use the graph in figure 20.2 to calculate the mass of the gas. So we know a formula which is given as PV equals nKT, where n is the number of particles and k is the gas constant. So if I just do PV over T, or theta in this case, I would, or rather also divide by k, okay, I would end up getting the value of n, and then I would end up multiplying this with the mass of each gas particle to get the overall mass of the gas. So for this, I need to consider the gradient of this graph. And so for the graph, I'm gonna take the full axis and full values, and this is 2.85 times 10 to the 2, bear that in mind. Okay, so it goes from 2 to 2.85 times 10 to the 2 over the change in temperature, which can stay in degrees Celsius, doesn't have to convert into kelvins, as the change is the same in kelvins as well as degrees Celsius. So the gradient turns out to be, this is a gradient, this is a value of PV over T, and that is 0.77. And I'm going to divide this by the gas constant, which is given to us. And this gives me a value of 5.6 times 10 to the 22 particles. And I'm going to multiply this by 4.7 times 10 to the minus 26 to get a value of 2.6 times 10 to the minus 3 kilograms. Okay, so that's part 1 done. Then it says calculate the internal energy of the gas at temperature of 100 degrees C. So I know that this is gas and the internal energy is equal to the kinetic energy, which is equal to 3 over 2 nKT, and I've got everything here. All I have to do is put it in the calculator. So for 5.6 times 10 to the 22 particle, and K being a constant, temperature has to be in kelvins, 373 kelvins, and that gives me 430 joules of energy. Let's move on to now question number 21. It says a stabilizing mechanism for electrical equipment on board a high-speed train is modeled using a 5-gram mass and 2 springs. For testing purposes, the springs are horizontal and attached to 2 fixed supports in a lab. Explain how the mass oscillates with simple harmonic motion when displaced horizontally. Well, that's because both the springs exert a force, okay, on the mass. So both springs exert a force on the mass, which is proportional to the displacement, okay, which is proportional to its displacement, okay, from its center or the resting position. So that's part A done. Part B is showing us the graph of displacement against time for the oscillating mass, and we have some undone kinetic energy curve graph, and the first part says determine the maximum acceleration of the mass during the collisions. So we know that A max is equal to omega squared A, where A is the amplitude. So 2 pi f squared times by A, which, let's see what the graph holds. So we know we need to work out the frequency, and for the frequency I am going to see how many waves are passing and then average it out, because I can see that the time period is not very consistent from peak to peak. It is here, which is 145-ish, and then 145. Okay, so let me just work out the overall. So we've got 1 complete wave here, 2 complete waves here, 3 complete waves here, and then another half. So 3.5 waves, and so 3.5 waves, and the overall time is 500 milliseconds. So 500, or well, I'm just going to leave it as milliseconds for now, and I end up getting 143 milliseconds as the time period. And so 2 pi over 0.143 squared times by the amplitude, which is I'm going to take it as that point, so 6 millimeters. So 6 times 10 to the minus 3. And that will all give me 12 meters per second squared. Then it asks us to calculate the maximum kinetic energy of the mass during the collisions. So we know that kinetic energy is half mv squared, but because it's talking about maximum, I'm going to have to calculate that Vmax first. So Vmax is equal to 2 pi a over the time period. So that is going to be 2 pi 0.006 over 0.143. Okay, pop that in along with the mass being 5 grams, so 5 times 10 to the minus 3, and square this answer. Okay, so square that. So I'm just gonna put this over here, and that ends up giving me 1.7 times 10 to the minus 4 joules as the answer. And part C now says, on figure 21.3, sketch a curve, or well, graph showing the variation of kinetic energy with time at a scale to your kinetic energy axis. Okay, well, the maximum is 1.7 times 10 to the minus 4, so I'm going to put that down here as 1.7 times 10 to the minus 4 and 1. Well, it's not going to have negative, so forget that. And what we know is that it starts off at maximum displacement, yes? So at maximum displacement, it will have 0 kinetic energy. So at each point where it passes maximum, okay, it would have 0 kinetic energy. And each time it will, so I'm going to have to just go in with this so that I don't make this mistake. Okay, let's just... Oh, that's not what I wanted, sorry. I wanted... And so we'll start off with... And where it's basically minimum right here, it would be 0 again. Okay, so it's... In the exam, of course, I will use better sort of, you know, scales in terms of doing it more accurately, but you probably get the gist that it's maximum where the displacement is 0 and 0 where the displacement is minimum or maximum. There we go. Job done. Right, that took like forever. Let's move on. So for part D now, we have to plan how you can obtain experimentally the displacement against time graph for oscillating mass in the lab. Include any steps taken to ensure the graph is an accurate representation of the motion. So you can either use a stroboscope or a motion sensor. I'm going to use stroboscope and explain how it would work. So stroboscope, essentially, you can set the frequency, okay, such that the positions of the mass are close together on one photo for accuracy. Then you take a photo to get different positions of the mass, and then you measure the displacement from the center and making sure that the camera is pointing at the equilibrium position. Okay, so those are some of the points to mention here. Righty, question number 22 now. Explain how Newton's law of gravitation is applied between two non-spherical asteroids. Well, we know that the gravitational force of gravity, is directly proportional to the two masses of the, well, two asteroids, the products of the two masses, and it is also inversely proportional to the square of the distance between them from their centers. I'm going to just leave it there. I know everyone can write this down, and this is the summary. So part B, a satellite moves in circular orbit of radius 15,300 kilometers from the center of the Earth. So just one main benefit satellites have on our lives, well, communications. Global communications is one of them. So part II, calculate the gravitational field strength G at the radius of 15,300 kilometers. So we know that because we are not given the mass of the Earth, we have to look for another method, and we can use the ratio, right? Because we know that gravitational field strength is inversely proportional to the r squared, the distance from the center to an object, and we can say that in order to work out the gravitational field strength at a distance of, well, 15,300 kilometers, we can just use the gravitational field strength of the Earth and take it as a ratio. So we know that the radius is 6,400 kilometers, and this is that. So because it's obviously inverse, I've flipped them around and then just square them and times it by 9.81. Simples. So it gives me 1.72 newtons per kilogram. Then for the next part, calculate the period of the orbiting satellite. So here, I guess I can use the acceleration, okay, as a way of working out the time period, because centripetal acceleration is v squared over r, where v is 2 pi r over t, okay, squared times by 1 over r. So if I just cancel out things like, so this is this, oops, 4 pi squared r squared over t squared r, boom, boom, and then t squared is equal to 4 pi squared r over a, and then square root it in the end. So 4 pi squared r, which is 15,300, 1, 2, 3, over a, which is 1.72. And that will give me a time period square rooted as 1.9 times 10 to the 4 seconds. Okay. Part C, determine the average density of the Earth. The radius is 6,400 kilometers. Again, because we don't know the mass of the Earth, I wish we were given. It's something so easy to remember, but we have to use the long way, first of all, to calculate the m. So m is equal to, well, I'm using g equals gm over r squared to make m the subject, g r squared over capital G, and 9.81 times 6,400,000 squared over 6.67 times 10 to the minus 11, and that gives me what I already knew, so kind of anticlimactic. So now density is m over volume, which is 4/3 pi r cubed, and again the radius being that, you know, cubing it, blah de blah, you end up getting the density as 5.5 times 10 to the power of 3 kilograms per meter cube. Simple. Right, let's move on to question number 23 now, where we have to state and explain how stellar parallax is used to measure distances in space. Well, so stellar parallax is basically apparent displacement or motion, change in motion of a star, okay, relative to the position of more distant stars when the Earth orbits the Sun. And we know that 1 arc second of parallax angle is the displacement of Earth, which is 1 astronomical unit, corresponds to 1 parsec of distance. Okay, so you just have to mention it thoroughly. So yeah, that's that. Figure 23.1 gives some data on the wavelength of a hydrogen spectral line for light received from the Andromeda galaxy and the Virgo cluster of galaxies. The Virgo cluster is 16.5 megaparsecs from the Earth. We need to estimate the age of the universe using the data from 23.1. Okay, fairly simple. We know that the age of the Earth can be calculated by doing 1 over h naught, and we know that v over d is equal to h naught, and we can calculate v by using Doppler effect, okay, which is the change in wavelength over the original wavelength times by the speed of light. So let's calculate v first, which is for the, I'm just going to use, well, this over here because this is receding, and so 489.8 minus 486.1 over 486.1 times by the speed of light, which is that, which ends up giving me 2.26 times 10 to the 6 meters per second. Now I'm going to work out h naught, which is, you know what, I'm just going to just put that in, actually, let's just do it step by step so that I don't lose any method marks. So 2.28 times 10 to the 6 over the distance, which is 16.5 megaparsec. So 16.5 times 3.1 times 10 to the power of 22, okay, meters. And that gives me a value of 4.45 times 10 to the minus 18 per second. And now I just have to flip it. So t is equal to 1 over that bit over here, duplicate it, and voila, I have the age of the universe as 2.2 times 10 to the power of 17 seconds. Part II, we have to suggest why hydrogen spectral lines might be used to measure a star's velocity. Well, that's because H is the most abundant element in stars, and so therefore the intensity received will be consistent compared to other elements which may not be present with in a lot of quantities. Okay. Part C. The Big Bang Theory is an explanation for the start of the universe. Explain how the cosmic microwave background radiation, CMBR, supports the Big Bang Theory for the start of the universe. Comment on the relevance of the data in figure 23.1 concerning the Big Bang Theory. So we know that at the start of the Big Bang, the radiation was mainly gamma, okay, gamma radiation, and it was spreading evenly in all the directions. And as the temperature started to rise, the stars started forming, and then the galaxies. And temperature further rose, and the peak wavelength decreased to reach the microwave wavelength. That's why it's called CMBR. And Andromeda, you know, if you go back up, Andromeda shows that it is blue shifted, okay, because the wavelength is shorter compared to Virgo. So Andromeda must be coming towards us, whereas Virgo cluster is moving away from us as it's red shifted. So that's basically supporting that the universe is expanding as the Big Bang Theory suggests. Okay, so that's about it. I think we've reached the end of the paper. Yep. So I hope you found this useful. I know I was supposed to do a paper 3 unified paper of the set 1 practice papers that I've been doing, but I decided to do this one as requested by one of you, and there aren't any videos being done about on this particular paper. So and your first paper is obviously paper 1, which is on the 24th of May. So I hope you found this useful, and very good luck to all of you sitting the OCR or, well, any physics A-level paper. I'll see you guys next time with another paper. Thanks ever so much for watching.